everyone. Hello, everyone. Please, my name is Greg Matthews, but you can call me Dr. Gregory Matthews. And I have tenure too. That's Kwong. I know exactly who that is. I guess I got to start out. I can't see anything, but I got to start out by doing this. Are there any ramblers in the house right now? Make some noise. Go Loyola. Go Loyola, right? All right. So they're all my students. All right. So I'm going to talk about shape-based classification of partially observed curves with applications in anthropology. And I'm Dr. Gregory Matthews, and I put a little. Hey man, how are you? Right. So this woman is Dr. Juliette Brophy. She used to be a lecturer at Loyola, and I met her when I first started at Loyola 7 years ago. And she's currently at LSU, and she got tenured, and she's like a big deal in the anthropology world right now. And I don't know if any administrators at Loyola are here, but they were stupid to let her go, and LSU's a better school anyway for anthropology, so we messed up. So Juliette is a biological anthropologist, and she's holding a picture that's Mrs. Plez, which is a famous fossil. I don't really know much about it, but that's her favorite picture. So what Juliette is interested in doing is studying early human behavior. Has anyone ever heard of the Homo naledi? One person. So she's really into studying Homo naledi. It's this really big deal. She's publishing in Nature about this. And so she wants to learn about early human behavior, right? And so one of the ways to do this as a biological anthropologist is to do something called paleo-environmental reconstruction. And so what you do is, if you can recreate what the environment was like, hundreds of thousands or millions of years ago, you can then figure out what the humans were doing, right? So if you know that the environment was grasslands, or if there was water, or if there was forest, you can recreate what the humans were doing, right? So in order to learn about that, you have to use fossils. And so in southern Africa, where she's doing a lot of her work, the fossil assemblage that is dominated by these kind of animals. These are called bovids. All right. I don't know the order of these. One is a Hippotrigine, one is a Trigelaphene, and one I think is Alcelophene. But I probably got that wrong. So these are like gazelles, right? And these are just living and dying all over the place. They've been around forever. And even though some of them may look the same, they have very different environmental needs. Okay? And so it's really important to be able to classify these things, right? I'm like 3 minutes into it, and then people are like, wait, this guy's a statistician? What's he talking about? So what would be really nice is if we were able to find full fossils of these guys, right? If we could find like a full dead skeleton from 100,000 years ago, and we could say, all right, this animal's a Trigelaphene, this one's an Alcelophene. We can get all the data, and we can recreate the environment, and Juliette can go on her merry way and learn about humans. But we don't have that, right? Fossils, when animals die, they get eaten, and fossils decay, and I don't know what I'm talking about. But what's left over, and what dominates the fossils is these isolated bovid teeth. So this is a picture of a tooth in a jaw. This is an extant tooth, and the idea of what we're trying to do here is we're trying to take these teeth, and we're trying to use those to classify the fossils that we have. So we take the extant teeth as a training data set, and we say, let's take these teeth, build a model, and try to predict the tribe or the species of this tooth, and then we can take that model and apply it to the fossils that we find, and then we can say, all right, this fossil belongs to this tribe, and we can do that for all the fossils we have, recreate the environment, right? Paleo-environmental reconstruction. The way we do that is by using the shape of the occlusal surface of the tooth. So we extract the shape of this tooth, and there's a lot of information in the shape of this tooth. Now, if we have a fully observed tooth right here like this, we can basically extract the points around the edges of this. So it's easy to go from a black and white image to extracting the edges. So we really are extracting the edges of this, and we're thinking of this as a closed curve, right? You can think about it as like being represented as like an infinite dimensional vector. That's how we're representing these shapes. If we have a fully observed tooth and we have the full closed curve, we know how to classify these things. We have techniques for doing classification. You can take the shapes and you can expand them using some sort of basis functions. You can pull out the coefficients of those basis functions and use those as features in machine learning models. Basically, the simple stuff, right? So if we have full teeth, everything's fine, okay? So when I first met Juliette, I was sitting around and I was like, well, as you probably know, I'm a missing data guy, right? I look like a missing data guy, so I do a lot of work with missing data. And I said, well, what happens do you ever have teeth that are fractured in half, right? And I go, so like, what happens if you have teeth like this? So these teeth are partially observed, right? So let's say I want to do the same thing. Well, because we're missing a whole part of the tooth, we can't do the same things that we did before. We can't just take the outline of the tooth. It's hard to see, but these are like half teeth, right? These are fossils and they're fractured in half. We can't just extract the outline and then run it through the other machine learning models that we have because these aren't closed. We don't have the full shape of this, right? We're missing part of the shape. And she said, so the question is, what do we do with these? That's the question marks. What do we do with these? So I was like, all right, we'll just go find in the literature someone who has done work with partially observed shapes and classification. And I started to look for it, and there really isn't much work done on like how to do classification or how to do any shape analysis when you're only observing part of the shapes and you're treating these as functions, right? If we were treating these as, if we were sort of representing these as landmarks, as like fixed points around the tooth, there's a lot of work done in sort of that framework. But when we're treating these as a function, and we're only observing part of the function, there's much less work done on that, right? So I asked her, where do these fossils exist? Do these exist? And she said yes, but they sit basically in a box in the back room of the museum and no one is doing anything with them. There are hundreds or thousands of these broken teeth that they just don't do anything with. There's so much information that they could be using that they're not. It's just literally sitting in boxes in the back of museums in Southern Africa, right? Crazy to me. Crazy. Right? What are they doing? They're throwing away all this information, okay? So what I wanted to do was to, because the method didn't exist, so we wanted to develop an algorithm for doing this kind of thing. So if anyone's familiar with the ideas of multiple imputation, the idea of, yeah, give it up for multiple imputation. Yeah. There's some Don Rubin fans in the house. Yeah, some Dempsey. Oh, okay, fair enough. I get that boo. I understand why. I've heard some stories. All right. So the idea of what we want to do is we want to be able to, the idea of multiple imputation is you take sort of what you have observed, and you're trying to build a model for the missing part of the data conditional on what is observed. So in a classic rectangular data setting, like Abby had shown, where she had the data set, like a rectangular data set, if some of that was missing, you can build models to try to predict the missingness, okay? Except in our case, our data is not records in a rectangular data file. Every piece of data we have is a closed curve. It's a function. And it's not even a closed curve, it's an open curve, right? We are observing, so what we observe is this black part. So all the black dots would be like a partially observed curve, okay? And so what I want to do is I want to figure out a nice method for completing that curve based on the information that we have. So this is going to be this is sort of a three-step process. So the first thing I want to do is I want to take all of the complete teeth that I have, and so one of the complete teeth would look like the gray dots would be a complete tooth here. So imagine I have a full set of complete teeth and I have a partial tooth. What I want to do is I want to take the black dots that I have, and I want to check what's the best matching that I can get for those black dots across all of the different teeth. So I want to align the black dots with all of the teeth in my data set, okay? That is a totally non-trivial step, but it's like the first thing I need to do. I need to align that, okay? The next thing I need to do is I need to calculate the distance between based on the best alignment, I need to calculate the distances between the black partially observed curve and all of the fully observed teeth. I'm going to use these distances as a measure of similarity, right? And so what I'm going to do then is I'm going to take these, I'm going to order them from like the closest, the smallest distance to the largest distance, and I'm going to then use, maybe I take the top 10 or the 5 closest to the 10 closest, and that's going to be my potential donor set, okay? I would then randomly choose one of these full teeth from that donor set, which is one of the closest teeth, and you would get the gray tooth. So the gray tooth is going to act as a donor, and that black tooth is going to be the donee. It's going to use the information in the gray tooth to fill in the missing parts of it. Okay. So once I've done the alignment, the matching step, I match the black to the gray. I then need to do completion. Okay, which I think is the next thing here. Complete. So what we're doing is we have the black points represent an open curve, and we've already matched it to this gray curve. So what I want to do is I want to use the unmatched part of the gray curve to fill in to complete this black curve. Okay. And so the way this basically works is the very first step. It's hard to see because it flips so fast. But the first thing we're doing is we connect one black dot to the other black dot with a straight line. It's going too fast, but we connect it with a straight line, and then it's like almost like a rubber band. And we then try to take that red line, make it flexible, and we try to match it to the unmatched part of the gray tooth, right, as close as we can, subject to the restriction that it has to match up with the ends of the black tooth. And this gives us an imputation for the tooth. So we're completing the tooth based on another tooth that's donating information about the unmatched part. Then what we do, as everyone knows about multiple imputation, you really don't want to do this once, you want to do this multiple times. So we have our donor set, right? We have our donor set of 5 or 10 or 20 teeth, however large you want to make your donor set. You randomly sample from that, say M times, and you get M completed data sets, right? And so this is an example of, this is simulated data. The left half is like we're saying, all right, let's try to complete this left half, and the right half are the true dots, but I'm pretending like I don't know that. When I go to do the completions, I get, these are 3 potential completions that I get. And the thing to notice here is that just using information from the left side, if you look at this, if you look at this, there's this third, it's like a half lobe right here. All of the completions are getting that half lobe. There's information in the left side of the tooth that is pertinent for the right side of the tooth. So what we can do is we can use this to do classification. And now what's happening is we're trying to broaden this. Classification is like one sort of analysis we can do, and we began doing this because of the application with anthropology, but now we're interested in more questions about, like, what about just general shape analysis? What if I wanted to, find the average of a bunch of shapes, or any principal component analysis on shapes? Anything that I want to do with shapes that needs a full completion, we're going to start looking at that, even if it's not, even if it doesn't have an anthropology sort of application. So that's where we're at right now. We've developed this algorithm. This just got published. It took me like years to publish this because this COVID thing happened and everything was a nightmare. But it just got published, and now we're working on actually taking this and applying it to a dig site in southern Africa called Gladysville. And Juliet's really excited about it. I guess it's important in anthropology. I don't know. I just do numbers. And then this is Abby. This is an advice for aspiring scientists. What you want to do is you want to take your collaborators' grants and you want to throw them in the last slide. It makes you look good. These are all NSF grants that someone is funded by on this project. Notice my initials only appear in 2 of these things, but it looks more impressive if you include your co-authors. And I had to put this GIF in here because this is a GIF that one of my students made of me, and I'm sure he's in the background now, smiling ear to ear because he's so excited that I used it in the slide. And these are where you can follow me on Twitter and Instagram and Facebook. Well, you can't call me. No, I'm unsuspended now, actually, so you can follow me on Facebook. And that is all I have to say. Yay!